Welcome everybody, and it's a pleasure to have Rodrigo Herrera Camus here. He is visiting us this week with the OS Visitor Program, and I'm very glad that he accepted the invitation. So Rodrigo is an expert in galaxy evolution, and you will see, regarding his work, and especially in the CRISTAL survey, but also just a brief introduction. He got his bachelor at Pontificia Universidad Católica in Chile. Then he moved to US, to University of Maryland, where he also did a PhD with Alberto Bolatto through a Fulbright fellowship. If I
Wow, you.
No, that's no. And then after the PhD, which he defended in 2015, he moved to Max Planck MPE, working in the infrared group there for 5 years. And then moved back to Chile, where he's now associate professor at the Concepcion, and he's also director of this Mingal group, that is a small research institute in Chile. And the meaning of the name, maybe he will tell you later. Yes. So he will tell us about stuff forming galaxies when the universe was 1 giga-year old, and so insight from the CRISTAL survey. And
No, thank you, Lydia. Well, thank you for having me this week and inviting me. I mean, I'm really enjoying this visit, and in particular, I have many things to show and discuss. Probably too many slides for a 45-minute talk, because since I'm going to be here this week, I thought I will just. Like you will tell me at 40 minutes, and then I will stop. But I will show everything that I miss, and then if you want to discuss about that, you can come to my office, which will change during the week.
Yes.
Lydia will know where I am.
The moment is that.
Okay, and then I'm there. But so you can come, and I will be happy to discuss, of course, with you. But then I'm going to show, also going to present a little bit tomorrow at the PISA lunch, so that then I will try to focus more on cosmic noon. But for this talk in particular, I would like to look at when the universe was 1 giga-year old, which at the time when we started this CRISTAL survey was really high redshift, but then JWST came, and now it's more like, okay, redshift. I mean, it's, it's not that high, but still 4 to 6, it's high. So I guess the first question that you're probably asking is, where is Concepcion? This is probably not as easy you heard. Thank you. So, well, where is Concepcion? And Concepcion is actually what is considered the south of Chile, but it's not really the south of Chile. The geometry, it's right at the center, but still in the south, it's south of Santiago. And then I thought, oh, maybe it's the southernmost astronomy department in the world, but no, I checked last night, and then we have Melbourne and Auckland over here. Both of them have astronomy departments. Of course, Swinburne University is here, so we share, I guess, the southernmost astronomy department. My dream after finishing my work at Germany was to go back to Chile and start like a Patagonia astronomical center, but it's just too far south, as you can see. I mean, it's kind of extreme. It's down here, so it's too much. So Concepcion is better. And since many of you are astronomers and go to Chile often, please consider to stop in Concepcion. I would be happy to host you. There are many lakes and beautiful places to visit, plus very vibrant astronomy department. So come to Concepcion. Okay, so this is more like a message for the graduate students here, the PhD students. 10 years ago, I finished my PhD. At the time, I was very interested in the ISM of galaxies. And for that, of course, you need to look at all the phases. And at that time, it was possible, thanks to Herschel, looking at the cold gas, Galaxies, giving us information on the ultraviolet emission of young stars. And from ground observatories, we could look at the nebular lines. So this was really nice because we could do these studies of multi-phase ISM in the nearby universe. When I finished my PhD, Herschel was about to finish, and I was very worried, like, what can I do? How can I find a job? I mean, I was really worried because all my expertise was on Herschel. But then, the good thing is that ALMA was online. And then with ALMA, of course, now you can move things to higher redshift. So basically do the same physics with the same lines, but now at much higher redshift. And I think we are in a very golden era now, because now from redshift 4 and beyond, you can use now ALMA to look at the cold gas and dust, Hubble to look at the UV emission, and JWST to look at the nebular line. So basically, for the same resolution, which is kind of sub-kiloparsec or kiloparsec scale, you can do the same science we were doing in nearby galaxies 10 years ago. You can do this when the universe was very young. So it's very nice and motivating. Of course, I'm interested in this time of the universe because, of course, this was a very critical phase in galaxy formation and galaxy assembly. As you can see, from redshift 2 to 0, galaxies already, most of them were mature, already form a disk, were massive enough and stable, while at redshift between 8 to 4, this was the end of the era of ionization. Mergers, of course, were much more frequent. Galaxies were much more gas-rich, so it's a very interesting epoch to study and understand in detail. And another thing that I could use to motivate why is this a very interesting phase is that if I show you this is a box, 450 kiloparsec on each side. And what I'm going to show you here is where all the stars that are at redshift 0 in the inner 10 kiloparsec of a Milky Way galaxy were at redshift 5. So it's all the stars you see in red. So basically, to build a galaxy like the Milky Way at redshift 0, if you look at the galaxy at redshift 5, you will have all these other minor companions, right, that need to find their way to the central part of the galaxy to actually form a Milky Way type galaxy at redshift 0. So that's a very important process that we need to understand at this high redshift to understand galaxy formation and evolution. And then the other process that is very interesting is, of course, the baryon cycle. So in this galaxy, the central galaxy over here, how is the gas moving inside the galaxy? Because it's super important to accrete gas to form stars and keep star formation, but also eject gas through outflows and then enrich with metals the CGM, recycle the gas, continue star formation, etc. So in this talk, unfortunately, I'm not going to touch much this part of the galaxy evolution process because I think in part it's very complicated and challenging. And now with NIRCam wide-field slitless spectroscopy, for example, we're making much more progress studying the environment of galaxies, but that's kind of new. So I'm mostly going to try to focus on the baryon cycle, and in particular, 4 areas. Kinematics, and one of the first questions it was driving my research when we started the CRISTAL survey was to understand when and how did the first rotate in this form. I think this is still a very important question, but we are closer to an answer, I would say. Morphology, in the sense that since we can look at all these phases of galaxies, the idea is, are all early galaxies irregular? How the distribution of the different components compared to each other? Then, of course, the ISM and the stars, the physical properties. This is something where JWST has been super important now, adding all the nebular line emission to the discussion. And finally, outflows, because as you know, outflows are super important for galaxy evolution. And this is something that we typically say, but have we really detected outflows in high redshift galaxies in multiple phases and measured the impact? This is something that was not so clear when we started this survey. So to really answer all these questions, we need different tracers from the different components of galaxies, starting from OV stars and the emission, the UV emission they produce, the H2 regions around these galaxies, then moving to PDRs and to molecular clouds. And I think if you look then at the spectral energy distribution of a galaxy going from redshift 5 to 6, we could say that we are now covering all these main optical lines with NIRSpec, the stellar continuum with NIRCam, some PHs with MIRI, and then, of course, all the main far infrared lines, and then some CO lines with ALMA and NOIMA. And in particular, one very important line is the ionized carbon line at 158 microns. And I'm going to stop a little bit to discuss this line in case you're not familiar with this transition, because many of the results I'm going to show are, related to this line in particular. So how do you produce this transition, which is one of the major coolants of the neutral gas in galaxies? So you start with an OV association, you produce FUV photons. These FUV photons interact with the dust via the photoelectric effect. They eject electrons, which hit the gas. The gas then collisionally excites your C+ ion, and then you produce a C+ photon. And the collisional partner can be atomic hydrogen, molecular hydrogen, or if you're in the ionized gas, could be electrons. So essentially, the origin of this line is multi-phase. And then if you assume that your ISM is in thermal balance, then this transition here, and the cooling is dominated by C+, which is most of the time the case, then essentially by looking at the cooling, you're also very well connected to the heating source, which is mostly star formation in these galaxies. So this line is multi-phase origin. It's very bright. It's the major coolant of the ISM and gives you a very good idea also about the heating. So it's a very powerful tracer of high redshift galaxies. I will say another big reason why this galaxy is very important is because if you now go back, 1993, Sue Allen paper with KAO, and then you see the galaxy, the stars in white, and the white contours here correspond to the C2. So you see the C2 is not only coming from the PDR regions in the galaxy, but it's also very extended because it's tracing the atomic gas in these galaxies. Why is this important? Because, as you know, in high redshift galaxies, we cannot access the H1 gas directly. I mean, SKA will probably look at the H1 gas maybe up to redshift 2, but no more than that. So basically, this C2 line is really maybe one of the few options we have to look at the atomic gas in the outer parts of galaxies at high redshift. In fact, if you look at the profile of the different traces in nearby galaxies, you see that H1, the radial profile is mostly flat. CO drops, of course, because it's following the star formation activity. And then C plus falls, but not as quick as CO, because in a way, it's also tracing the H1 in the other parts of galaxies. So C2 is also a very powerful alternative. Look at the extended gas in galaxies at high redshift. And finally, cold gas. Why? Because when you want to study cold gas in high redshift galaxies, unfortunately, we need to rely, if we're going to use ALMA, for example, on very high JCO transitions, and which are not tracing the bulk of the molecular gas in many cases. And you also have the problem of metallicity. So as metallicity decreases, a larger amount of molecular gas is not traced by CO. This is what we call the CO faint or CO dark gas. And then this is not the case for C+. So C+ is also a very good alternative to try to look at the cold gas in high redshift galaxies and then understand, for example, the star formation efficiency, if the Koenig-Schmidt relation that we observe in nearby galaxies hold at high redshift, like everything that Livia is studying. So the C+ is also a very good alternative to look at the cold gas. And in fact, because this is sometimes something hard to study high redshift galaxies in detail, together with a master's student at Concepcion, we are leading a survey on the Small Magellanic Cloud, and we are really looking at regions with low metallicity comparable to what you see at high redshift, trying to understand how much of the molecular gas is faint, and it's only traced by C2. And the number we find in the Magellanic Clouds is around 70% of the molecular gas is actually not traced by CO, it's traced by C2. So this could be also, I mean, this is very important, and we need new ways and more ways to study this in more detail in nearby galaxies so we can understand better how to interpret high redshift results. Okay, so the studies of C+, of course, became very important as soon as we have ALMA, and there were a few papers looking at small sample of galaxies. Then there was this very large program called Alpine, which was very important for our field because we then moved from like 0 normal star-forming galaxies of C2 to 10, and then to 88, and this was great. The only problem was that all these observations were unresolved. So while with JWST, for example, you could look at the structure and the stellar component of galaxies, C2 was always more like a blob. And of course, this was not ideal. And then in my astronomy department, we have people working on the Milky Way. They will always make fun of me because we were using these blobs. And in a way, that motivated me to start the CRISTAL survey, which was an ALMA large program selected to follow up galaxies from this successful Alpine survey, but now try to reach kiloparsec scale resolution in order to match the JWST resolution and then have like a multi-phase characterization of high redshift galaxies. So with CRISTAL, we were able to go from that blob to now actually resolve the galaxies, which in this case, it looks like two important components over here, plus a lot of extended emission around of the galaxy, which is something you will see next. So the CRISTAL, in a nutshell, I mean, we published the survey paper this year, and there is also a website where you can find the list of all papers. We were targeting these galaxies with the C+ line and the dust continuum. We targeted initially 19 main sequence galaxies, but because we went very deep, we actually detected 35. And in the field, we also have 2 dusty star-forming galaxies, which have beautiful data because it's very deep and these galaxies are very bright. So, I mean, if you're interested in dusty star-forming galaxies, you should consider looking at the tool we have in our survey because there's a lot of things you can do with this. These are main sequence galaxies, like normal, kind of massive. I mean, the cut is at 9.5, but we were able to detect some at 10 to the 9. Most of these galaxies have NIRCam data, and then there was a program, a follow-up, NIRSpec, led by Andreas Feist, which recently appeared on the archive together with Seiji Fujimoto paper on the data reduction, I think 2 days ago. So now we also have a NIRSpec component with information of the optical lines. So this is the family picture of the crystal galaxies. They are all of them at the same scale in this. As you can see, the first thing you can see, I mean, we didn't select by morphology or if these galaxies were interacting. It was really more like a stellar mascot. So some of the crystal galaxies are interacting. Some of them have this extended emission that, of course, we didn't know before. Like crystal 13, for example, you find the galaxy. If you look at the JWST image, all the stars are here, but still there is a lot of extended gas around this region, which you can see here. So then this is now showing the stellar component in the background, and then in white, you can think of this as the cold gas, and you see it's typically more extended, similar to what I was showing you before with the H1 vanishing in nearby galaxies. So when you look at a galaxy with JWST NIRCam, you're only seeing one part of the galaxy, the stars. But just think, if you look at that galaxy with ALMA, you will probably see much more structure because you're looking at the gas around these galaxies, which is key. So JWST just half the picture. You need ALMA to have the whole picture. Okay, so now I'm very happy. I mean, I'm very proud that we finally have, because of the community work super hard, a very good amount of data going from the UV to the stellar light, the optical lines, the cold gas, the kinematics, and the dust continuum for galaxies between redshift 4 and 6. So what we're currently doing right now, and I have a master student who is leading this effort, is basically creating a database where for each one of these spaxel, which are about, let's say, sub-kiloparsec resolution, we will have a catalog of more than 1,000 independent regions where you will have all this information available, plus the SED modeling, which gives you information, for example, about the stellar mass. And all this will be available for the community. Plus, we're adding Serra galaxies, which we're treating like crystal galaxies with all the observational effects. So we believe this database will be very useful for people if, for example, you want to compare your own galaxies at different redshift, etc., with what we have between redshift 4 and 6. But this is a dream for me. Like when I finished my PhD 10 years ago, this was only available for redshift 0, and now it's available for high redshift. So it's a lot of work. And of course, it was not only me, it was a lot of people contributing to this. Okay, so let's go back to the science goals of this survey. So I mentioned kinematics, morphology, ISM, and outflows. So let's start with kinematics. So this map over here, this figure, is showing as a separation from the main sequence. As you know, crystal galaxies by design are a factor within 3 of main sequence. The velocity field as a function of stellar mass. And this work was recently published by Lillian Lee, a PhD student at MPE, working with Natasha Förster-Schreiber. And as you can see, some of the galaxies have beautiful velocity fields, like this one here. Other ones are more dispersion dominated. So we actually look at those, for example, that have rotation from the velocity field. We were able, of course, to extract rotation curves, as you see here. And then from the rotation curve, you can model, and then you can get important information. For example, the rotation velocity and the intrinsic velocity dispersion. I asked Lillian to prepare this plot because I was always so inspired by the Vera Rubin 1987 plot of redshift 0 galaxies. And I don't know if you're also happy like me that now we can do this for the redshift 5. I think that's also that we have the same quality data, but at high redshift. So then the next step was to look at the galaxies and do a more deeper analysis based on the morphology and the kinematics. For example, you can use the kinemetry method and other methods to try to understand which galaxies can be classified as disk, which you see here in red, or those that are non-disk. So basically, if you look at the disk fraction as a function of redshift, the black and the white is what has been observed with NIRCam. But again, this is in a way only limited information because then you have to classify a galaxy as a disk only based on the morphological appearance. This is a much complete way to look at the classification of a galaxy. So what we find is that based on the morphokinematic analysis, around 50% of main sequence star-forming galaxies between redshift 4 and 6 can be classified as disk. This is consistent with what has been observed also with the imaging. Now, this is number I was surprised at first. I mean, it's only 1 gigayear. The universe is only 1 gigayear old, and the fraction is already high. But you need to remember also that we are selecting main sequence galaxies. For example, maybe if you look galaxies above the main sequence, these will be smaller because these galaxies are interacting, and that's why they are above the main sequence. But again, for main sequence galaxies, still, it's a good number. Now, in order to try to understand a little bit, just not to classify, but look at the physics of what is happening, one very simple thing we can do is we can look at the classic Tumre parameter for the stability of the gas. And then if you express the total dynamical mass of the system based on the rotational velocity, and the total gas mass of the system based on the gas mass, which you can get from the C2 line, then you can relate the Tumre stability parameter to this important parameter here, which is the dynamical support. So essentially what you do is you compare the rotation velocity of the galaxy and the turbulence, or the velocity dispersion. So if a galaxy has a value of B over sigma much greater than 1, it means that this galaxy has a very mature dynamically cold disk, like the Milky Way. For example, the Milky Way has a B over sigma value of around 10. If you have a B over sigma lower than 1, that means that your galaxy is more like dispersion dominated. And then this, as you know here, if you compare to dynamical mass and the gas mass, this could be expressed as the fraction of gas in the galaxy. So you would expect that B over sigma goes as 1 over the fraction of gas. So as you go to higher redshift and galaxies are more gas rich, then your B over sigma will decrease. The question is, at redshift 5, 6, 7, would it still be above 1? So you have rotationally more dynamically cold disk or no? Now, that's a very simple picture. There are more complex pictures. For example, there is the model by Krumholz, 2018, that also includes the radial transports of gas, which is important, as I will show you. So if we include gravity and feedback, well, let's start with feedback. So you know there will be supernovas, star formation, supernova, the stars will explode, and they will inject some level of turbulence that you would expect from energetic arguments, that it will be between 10 and 20 kilometers per second. So that should be your floor, because you have active star formation. But then you can also have additional sources of turbulence, because of course you have instabilities that produce clumps. These clumps start to migrate towards the central part of the galaxy. They release gravitational potential energy and inject turbulent motions. So then, just using this more complex but still kind of a simple picture of analytic picture, then you can connect the B over the B and the sigma of the galaxy with the star formation rate and the fraction of gas. So what we find, let's go first to the observations. With the observations, what we find is that starting at redshift 0, the velocity gas dispersion starts to increase. So galaxies are more thick and more turbulent as you increase your redshift. And then, of course, these are the crystal galaxies you see here in black with the green line around. So high redshift galaxies are more turbulent, and the velocity dispersion we measure in these galaxies is between 60 and 100 kilometers per second. Now, how to explain that? Well, let's go back to the model I told you about transport plus feedback. So for the analytical expression that I showed you before, if you assume constant for nearby galaxies and high redshift galaxies, this is what you would expect. So there is a floor, which is given by the star formation activity, and then the dispersion goes up as there is more and more radial transport of gas towards the central part of the galaxy. So the crystal galaxies are over here. Their dispersions are definitely higher than what you would expect from, for example, just star formation activity. And the only the way to really explain this high velocity dispersion is that if these galaxies are gas rich, and there is radial transport of gas towards the central part of the galaxy. So this is one of the most important conclusions, I would say, from the survey and the kinematic analysis. Now, if we now look at the dynamical support, so B over sigma, remember, Milky Way type galaxies, redshift 0 are around here, around 10. And as you remember, this will, based on the Tumre theory, right, goes down as the fraction of gas increases. So the crystal galaxies, let's say, tend to have B over sigma values of around 2. There are some cases where we find that redshift 4 galaxies with B over sigma around 10. Those were published by Francesca Risso. So this was also a very maybe unexpected result, that we will find galaxies with such high B over sigma values this early in the universe. And it shows that you can create, I mean, with 1 gigayear is already enough time to have dynamically cold disk in the high redshift universe. So there is a high contribution. So the V over sigma goes down. But this trend over here is consistent with what you would expect, that as galaxies become more gas-rich, this V over sigma value goes down. But still, for about half of the crystal galaxies, is above 1. So these galaxies could be considered as disk. Now, another very interesting quantity that we can measure for those galaxies with beautiful kinematic maps and where you can do the kinematic modeling is the dark matter fraction. So essentially, you model these galaxies taking into account all the observational elements, and you can measure the dark matter contribution at a radius of 1 effective radius, and then you measure the dark matter fraction, which for the crystal galaxies is about 20%, consistent with the trend observed, for example, at cosmic noon and at redshift 0 of decreasing dark matter fractions. This also is consistent with, for example, what you see in elliptical galaxies in the nearby universe, which have very small dark matter fractions. And you need to remember that these crystal galaxies are on the massive end of star-forming galaxies at redshift 5. So they most likely will become elliptical galaxies at redshift 0. And this, in a way, is showing that the baryon fraction, or richness in the central part of the galaxy is already in place at this high redshift. Okay. Good. Now, another very cool thing you can do, if you have now the metallicity and the metal distribution because of the NIRSpec spectra, is then you can look and try to connect the metallicity gradients in the galaxy with the kinematics. Because, for example, if your galaxy is very turbulent and it has outflows and it's very active, you would expect that the metals will be redistributed in a kind of short time scale in the galaxy, right? Well, if you have a more settled galaxy, close, for example, to a very dynamically cold disk, you would expect a nice, maybe negative gradient and metallicity gradient. So what this plot is showing is the metallicity gradient over here, like no metallicity gradient around 0, then positive or negative, as a function of the velocity dispersion and the rotationally support parameter. So what we find in the crystal galaxies is that we don't see any strong evidence for example, negative metallicity gradients. In fact, most of the galaxies have no gradient, or maybe even some positive gradient, no trend with velocity dispersion. I mean, this I would expect if a galaxy is very turbulent, you should not see a metallicity gradient. And then compared to V over sigma, again, no strong trend. Velocity gradients of these galaxies are typically flat or maybe slightly positive. So the explanation for this could be one of these two or the two combined. So we have, for example, accretion of metal poor gas that is going towards the inner kiloparsec region of these galaxies, and that's why you see a positive metallicity gradient. Or you have galactic outflows with a high mass loading factor that are then removing the kind of more metal-rich gas from the central part of the galaxy and redistributing that in the galaxy. And that could be the explanation for these metallicity gradients we observe in these galaxies. Okay, let's move now to morphology. Only have 15 minutes. So, but then I'll just show you the slides very quick and you can come to my office. So, sizes. As I showed you before, C2 should be much more extended than just the star formation, the star forming disk of galaxies, because C2 is really tracing also the more extended gas. So one of the first things we did was to look at the sizes, for example, of the dust from the ALMA dust continuum and the UV emission. So in this plot over here, we have the effective radius measured in the UV, so essentially young stars, and then the dust. And what we find is that these crystal galaxies or main sequence galaxies of redshift 5 tend to have sizes in dust continuum that are larger than the UV. And very importantly, if you then look at the fraction of the star formation that is obscured by dust, that you would expect maybe, oh, these are high redshift galaxies, there should not be a lot of dust obscuring the star formation. Well, it's not the case. So we know there is a trend of this fraction, how much of the star formation is obscured by dust. With the stellar mass, more stellar mass are more dust rich, and therefore they obscure more star forming photons. And there is also a trend with redshift. Given that for of course lower redshift, there will be even a higher fraction of star forming photons obscured. in CRISTAL, we find that the amount of star formation activity that is obscure goes from like 20 to 80%, which is still a significant number for galaxies in this early phase of the universe. Now, I know these are massive galaxies at this redshift, but still, in the more massive cases, 80% of the UV photons are actually obscure, and which is a very interesting result. Now, if you now compare the size of the C2, so just think of the cold gas, a mix of molecular and atomic gas around galaxies, to the UV, so like tracing, if you think maybe it's tracing the star-forming disk, we do find that typically these crystal galaxies have 4 or even 8 times larger UV effective radius. So the emission is much more extended. Now, is this extended emission a halo component or an extended disk? This is something we can check if we model in the UV plane, the emission from the C2. So if there is a component that you will consider a halo, like a break from a single exponential profile, then you would expect like one of these points on this very short UV distance that is very high, but we don't see the case. So in the crystal galaxies, the emission is extended. It's very extended, as you can see here, but it's more consistent with a kind of extended disk that really a break. Now, there might be a break, but the data we have is not deep enough yet to detect that break. And we do have some programs approved for the next ALMA cycle to finally go deep in compact configuration to try to look at the more extended emission that might be tracing the CGM in these galaxies. And this is consistent with what I showed you before from this 1993 paper, that really the C2 is tracing also the extended gas around the star-forming disk of high redshift galaxies. Now let's go to the ISM. And I want to make this point because now doing SED modeling is like super important because we have beautiful near-term data and we all do SED modeling. And I want to show you what happens when you add one ALMA dust continuum point to your SED model. Because for the crystal galaxies, we not only have all the HST and build near-cam, we also have a dust continuum point at 160 micron. And this work was led by Juno Lee, a student of Elisabetta Cunha. So using MACFIS, he modeled the SED distribution of the galaxies, measured different quantities, including the specific star formation rate, which is the ratio between the star formation rate and the stellar mass of the galaxy. And I'm going to show you one example that is very clear that including the ALMA dust continuum is very important. So if you look at this crystal galaxy over here, and you just model the specific, measure the specific star formation rate without including the dust continuum of ALMA, you find a trend that is decreasing as you go outside from the center. So evidence for, let's say, inside out, you could say this could be inside out quenching for this galaxy. But then if you include the dust continuum, these trends just go away. And this is more like a flat distribution. So what we find is that, of course, including dust in the SED modeling is very important to break the age dust degeneracy. So I'm not saying that all the SED are wrong on the literature, of course not. But I'm just saying that it's really nice that we try to go for this more multi-wavelength approach where we can include the dust continuum to, for example, fix these problems that can appear when we just do SED modeling based on the near-cam data. Another cool thing you can do, finally, is to look at, for example, the IRX beta relation. And if you're not familiar with this, so IRX is really the ratio between the far infrared luminosity and the UV luminosity. So that's what you see on the y-axis over here. And beta is the UV slope. So also it's giving you an idea on the dust obscuration. And what we find so these are the typical relations that you see, for example, in the SMC, in dotted lines, and in more like nearby star-forming galaxies. All the points you see over here are kiloparsec regions. So now we can study these IRX beta relations on spatially resolved scales at high redshift. And what we find is that there are many regions actually with very high IRX beta values, which is consistent with, in a very simple picture, essentially that these galaxies have an ISM where you have dense regions of star-forming activity that are dense and completely obscure, bright and infrared, but also with holes that would allow the UV photons to escape and produce these values with low UV slow, but high IRX value. So this is led by my master student Mauricio, and the paper is soon to be submitted. Okay, and now let me show you this beautiful example. Just one example of a galaxy where now at redshift 5, I don't know if you share my excitement, but it's been years, right, that we've been trying to do this at redshift 5, and it's finally possible, where we have all the pieces of the puzzle. We don't have an answer yet, but we have the pieces. So, for example, let's look at this case, HC10 at redshift 5.6. It's a galaxy for which we have multi-band ALMA continuum observations. Thanks to NIRSpec, we have metallicity. So this is a metallicity map. This galaxy has 3 components, and the metallicity is about half solar, as you can see here. We have the stellar emission, in this case, from the continuum. And this is one of the few galaxies at high redshift, like a main sequence galaxy at this redshift, which are with a CO detection, which gives you an idea of the molecular gas, having in mind that, of course, there could be the problem of metallicity. So now that we have all the pieces of the puzzle, we can start finally trying to understand how much dust, how much molecular gas there is in this galaxy, what is the relation between dust and metals, etc. I don't have time to go through all these different results, but I'm going to show you this one, which I'm very happy that we finally have. This is an SED going from band 10 to band 4. If you don't work with ALMA, oh my gosh, getting the band 10 data was tough. Like, it was multiple cycles of trying until ALMA changed their policy, and they really said, we need to prioritize band 9 and 10 observations, and then it happened. We finally got the band 10 data. And I was excited because I thought, yeah, with band 10, we will finally have the information about the peak of the SED, which, yeah, we don't know. Like, if you look at this point, we don't really know if that's the peak. We don't have band 11, unfortunately, or band 12. So, I mean, it's an unsolved mystery. But at least with this very nice SED, we can now constrain the SED. Maybe this is similar to units in the nearby universe, where you actually need 2 components, like a warm component that will fit this part over here, and then a cold. I don't know, but at least we can measure a dust temperature, about 30 Kelvin for this galaxy, a very reliable, robust dust mass, 10 to the 8. And then if you compare that to the metallicity, so you look at the dust to gas ratio and the dust to metal ratio, what we find is the following. So this galaxy has about half solar metallicity, the star over here. These galaxies over here, these are more local, nearby galaxies. So what we find is that at half solar metallicity, this HC10 galaxy at redshift high has less dust than expected compared to gas and compared to metals. So essentially what this suggests is a delayed buildup of dust, potentially due to inefficient ISM dust growth. I mean, that's one possibility. But it's really nice that we can finally start doing this type of analysis that were very common in the Herschel era for redshift 0 galaxies, this time at redshift 5. Now we can also do another component of the ISM, which are electron densities. And this, thanks to the NIRSpec data and the sulfur line doublet. So my PhD student, Nicole, is working on this. We do find a trend, as have been observed in other works based on JWST NIRSpec data, of increasing electron density with redshift. So CRISTAL alpine galaxies tend to have electron densities that are above 100 electrons per cubic centimeter and up to 4, with an average of about 10 to the 3. And then there is no connection really to sigma Cephar. I mean, there is no clear trend. In nearby galaxies, you typically observe a trend between sigma Cephar and electron density because, of course, if you have higher sigma Cephar, then you would expect more compact H2 regions with higher electron density. But again, the scales are different. Physical scales are different, but we don't see any significant trend with the data so far for these high redshift galaxies. So finally, outflows. I think I'm going to make it 5 minutes. Excellent. So outflows. Outflows are multi-phase. This is something we need to remember. And it's very important, in my opinion. I mean, maybe I'm biased because I'm showing a paper that I published in 2020, but if you look at units, for example, and then you look at the different phases of the gas in the outflow, molecular, ionized, atomic, multi-phase, and total, then you realize that most of the mass, for example, is in the cold gas. And it's the same for the mass outflow rate. So this is comparing the mass outflow rate and the star formation rate. So when you're only looking at, of course, the ionized phase, it's very important for the energetics. This is warm gas, and I understand that. But in terms of mass, you might be missing a very key component. Of course, doing the molecular gas high redshift is complicated, but that's why we have the C2. So it's another example, just to motivate why we need more C2 observations of outflows in galaxies. If you look at M82, it's a beautiful example of a galaxy where you, of course, see all the multiple phases of the outflow. This is us now going back to the nearby universe and trying to promote some results coming from JWST. If you look at this beautiful map with NIRCam, published by Rebecca Levy in 2024, now we're able to look at the star clusters that are actually driving these outflows, characterize them, do all the energetics balance, and try to understand, how far can they push the gas, etc. And you need to remember that, of course, when now go to high redshift, all these stellar clusters that you can measure in nearby galaxies will kind of look more like a giant star-forming clump at redshift 5. But still, you can do the connection now between the high redshift and the low redshift. And just to show you something to inspire you that unfortunately we cannot do a high redshift, but we can do a redshift 0. This is a NIRCam MIRI map of the pH emission in the outflow of M82. It's just beautiful. So you see the central starburst, and then you see the outflow, and you see all the filamentary structure of all the dust in the outflow. That is, if you look at the papers from this team that I'm part of, the pH emission here is tracing very well the molecular gas. Now, of course, at high redshift, we don't have this detail. So that's why I keep working with nearby galaxy people, because I really need this to get inspiration to then go back to high redshift, where we don't have this resolution, but we're getting there. I mean, it's not, we're not doing that bad. Let's look at this example, for example. This is CRISTAL 2, 3 giant star-forming clumps. So you need to remember, this here probably is like a collection of star-forming clumps in the central part of M82, but now you see this as a giant star-forming blob. So if you look at the dispersion velocity map, you see a bicone type of structure with high velocity dispersion, and you see broad wing emission. So most likely this clamp over here is driving an outflow that we detect in both C2, so the cold gas, and the warm gas, thanks to O3 and H alpha. Now you can also do stacking. So for example, if we stack all the crystal galaxies, this was done by Jack Birkin, we also find evidence for outflowing gas in cold gas with velocities of about 300 kilometers per second and mass loading factors of about 0.5. And I would like to finish my talk showing you this beautiful example that is not published yet, but I should publish soon, which is this galaxy, CRISTAL 8 from the survey, that, as you see, has multiple giant star-forming clumps. And then in white, that's the cold gas distribution in this galaxy. We can do the SCD modeling. We can look at the properties of these different giant star-forming clumps. They typically are very massive and have stellar ages of about 100 million years. Some of them are more mature, 200 mega years. But what is interesting is that then you can look at the C2 spectra, and we find evidence for outflows. In fact, with velocities of about 300 kilometers per second. So if you look at the velocity of the outflow as a function of the mass of the giant star-forming clump that is driving the outflow, this is the case of NGT C253 over here. And these are the crystal, the outflows produced by the giant star-forming clumps in CRISTAL 8 and CRISTAL 2, the example that I showed you in the slide before. And this in gray is the expectation from a simple relative pressure model that was published by Murray, which essentially connects the velocity of the outflow with the mass of the giant star-forming clump that is driving the outflow. And you see there is this very good agreement between the model, the expectations, and also the connection to nearby galaxies. So I think we're finally at a point where at high redshift, we can look at outflows driven by a star formation, connect those to nearby galaxies, and try to understand also what will be the impact of these outflows. So because, for example, because we have the C2 information, in a way you can measure the depletion timescale, right? If you assume the C2 is tracing the cold gas, and then you measure how fast the gas will be depleted, in these outflows over here, we find that the time that will take the outflow to eject the gas is actually short, between 30 to 60 megayears, much shorter than the depletion timescale and that the age of the giant star-forming clumps. So these clumps, based on these very basic assumptions, will most likely be destroyed before reaching the central part of the galaxy, which is one of the theories, how do you form a bulge in high redshift galaxies? So a few words about the future. I mean, I found this paper by Seiji Fujimoto, The Cosmic Race, very inspiring, because as you can see here, this is a lens galaxy where you can identify many star-forming clusters. But then if you de-lens the galaxy and you imagine you are looking at this with NIRCam for a non-lens galaxy, it's just one giant star-forming blob, which I think is the case, what we're seeing in CRISTAL 8. But ELT is coming. It's being built. It will offer 6 times better spatial resolution than James Webb and 16 times better resolution than HST. So once ELT is ready, in 5-6 years from now, we will be able to go from these blobs we're studying in CRISTAL 8 to really break these into smaller giant star-forming clumps and connect that to the outflow. So that would be super exciting. The second thing about the future I would like to say, and this is my last slide, is that if you look at this is a compilation of galaxies that has been observed with James Webb in gray over here as a function of cosmic time and UV luminosity. And then in color, you see the galaxies that were targeted with ALMA, thanks to the Alpine Crystal surveys between redshift 4 and 6, reverse between redshift 7 and 8, and this recently approved ALMA large program Phoenix that will go up to redshift 13, 14. So as you can see over here very clearly is that so far with the current capabilities of ALMA, we can only follow up the most massive system at high redshift. Still main sequence and typical galaxy, which is great, but the most massive ones. And we're still missing all these other galaxies over here that are lower mass. So for that, I think maybe thinking of a very big upgrade to ALMA, this is part of the ALMA 2040 plan, would be a very good idea. Otherwise, I don't see a way that we can follow up all these very interesting systems we're detecting with James Webb, especially if you want to do spatially resolved information that I hope, as I showed you in my talk, is very important to understand what is going on. So I would just leave you with my summary slide of all the things we have learned in galaxies between redshift 4 and 6, thanks to the combination of ALMA, James Webb, and Hubble. Thank you.
Thank you very much. So